Okay, so in this lecture we will learn few more examples about modeling, again using all the steps of modeling that was listed earlier to see if we could still identify basic elements. Again we go with conservation laws or any of those physical laws that govern the system, right. Okay, so the first example that we will deal is very simple model of a cruise control of a car. So cruise control refers to the control of a velocity of a car on a road, where the input comes in the form of some kind of an accelerating force. The measured output is usually the car velocity, and then we usually measure the position of the car, how much distance it has traveled, typically from reference point. Okay, so how do we capture this dynamics, that there is a certain force which generates a displacement and in turn a velocity. Okay, so if we go back to the steps of modeling, the first step would say, well, what is the purpose of the model? Well, the purpose of the model is to understand the velocity behavior of a car and therefore to control the velocity. How do we define the boundaries? Well, we look at the car as the system to be controlled, and then it travels on a highway or a road that forms a part of the environment. Okay. So what could be a typical structure here, right? So there is again a force, a displacement and velocity. So we could say that in this system the thermal energy which comes from the engine structure is converted into kinetic energy or the velocity. Some part of the energy is lost due to friction between the road and the car. We will not take into consideration for simplicity the thermal losses in this car. So the car would have a certain mass, right, and then since we already said that there is some energy lost, there should be some kind of a damping element introduced in the model, right, and before we write down the relevant energy conservation or the force conservation loss, right. And also, to be a little simple to begin with, we will neglect the rotational inertia of the wheels. Okay. So once I do this, I would like to select some basic variables of interest, right. So the variables of interest are the displacement x, which again gets a velocity, all via this force F. So I have this car modeled as a mass m, and the friction between the car and the surface on which it is moving, the road, as modeled as a damper with a B. Okay. So there are two elements here. One is the inertia element, which is modeled as F equal to mx double dot, as we did in the previous lecture. Frictional force would be related to the velocity via a damping coefficient B. Okay. Are there any physical laws? Well, once we identify this structure and the structure here, I can directly write that the summation of all forces is 0, which means something like this. This is my external force, the frictional force and the accelerating force. So what is the frictional force? Well, this is Bx dot, and the accelerating force is mx double dot, and substituting that dx by dt is the velocity. I can write my equation as F minus B times V minus m times V dot, sorry, F minus B times V would be equal to m times V dot, or the final mathematical model would look like V dot plus B over m times V is F over m. A very simple model which captures the cruise control in a car, right. This is very simplified model, but still gives us some basic understanding of the dynamics of the system. Okay. The next example, again we come back to the electrical domain, is that of a transformer. So what is again transformer? Just to recollect, it is an electrical device which transfers electrical energy from one circuit to the other, and it works based on the laws of electromagnetic induction introduced by Faraday. Now how does it look like? Well, it has a core, something called a primary winding and a secondary winding, and energy transfers happens by inducing voltage in the secondary winding via the core. And where does the core get that energy? The core gets its energy through some electrical source in the primary winding, right. So if I just quickly write a very small diagram of this, I could say that this is my core. So I have all this as my primary winding, this is my secondary winding, I have voltage source, and then so I will call this Vi, which will generate some output voltage Vo here, and then this is the magnetic core, so there will be some flux, and with all those electromagnetic induction loss, there will be a voltage induced in the secondary, and then you will have certain Vn1, N2, such that V1 over V2 is again N1 over N2 equal to I2 over I1, and then what is the relation between the power here and the power here? If I just write it very simply, the input power should be equal to the output power, or V1 I1 is V2 I2. Okay. Now this is something which we do in our course, right? All textbooks have some problems like this. Consider a problem where I have given a rating of a transformer that 200 to it goes from 200 to 400, a step up transformer, frequency is given to be 50 hertz, single phase transformer, some power factor, and you say calculate the efficiency of the transformer operating with a load, with some load, right, at 100% load, at 80% load, 50% load, and 20%, 25% load. Okay. So, how would I solve this problem? Do I take this transformer and say, well, let me get a voltage supply, let me get a load which is 100%, and then do my experiment each time for 100%, 80%, 50% and 25% and get the answers? Or there is any other easier way? The risk when I do these experiments is that I could, well, I may not be very careful, or I could burn down the transformer and so on. And therefore, what we equivalently see this problem is a problem translated to something like this, right, which is the equivalent circuit model of a transformer. Now, once I read this question, solving it through this picture seems very tricky, right, that I really have to get this transformer down, open all the wires, get a big crane, because this looks a very big transformer. But if I look at this transformer as something like this, then things get much easier. Now, what is this process called? This process is where we call what we call as the model of the transformer for solving problems of this kind. And why do problems of this kind arise? When we say that V1 by V2 is N1 by N2 or I2 by I1. If this was true all the time, then we would never possibly need an equivalent circuit, because this thing usually does not, it is not always true that V1 V2 is I1 I2. There is something going wrong here, and that something going wrong is what we will try to observe. Okay. So, we will propose a model for analyzing losses, and therefore, we could, and in turn we could compute what is the efficiency. So, the first step we identified what is the purpose, second step is define the boundaries, which is a transformer possibly connected to a load, and then the structure. Well, the structure of the transformer, so we have the primary winding, we have a secondary winding, we have voltages, currents. Now, since I have winding would have its own resistance, its own inductance, the core would come with its own properties which might lose some energy and so on. And okay, just for a moment we will assume that we will neglect the saturation of the core. But if I take into consideration all these other things of what in the textbooks would be called as the core losses and the copper losses. So, I then give a structure to that, right. So, I have a primary winding and a secondary winding. Then I call this, well, each of these guys would have some resistance, let me call this R1 and R2. There would be some flux leakages in both the windings of primary and secondary, I will call them as L1 and L2. There are certain losses which happen in addition to the losses in the winding also in the core. They are, I will quantify them as R0, the resistance which quantifies the heat loss in the core, and similarly the inductance of the core, right. Okay. So, once I have this beautiful looking circuit, right. I have a voltage source, a resistance, L1 the inductance, R0 I have L0, I given here the turns ratio, L2, R2 and so on. So, this is the physical model of the transformer. Now, given a transformer, who tells me what is R1, L1, what is R0, what is L0, what is L2 and so on. The load I would know because I am just connecting this externally to the transformer. Okay. So, once I have this equivalent circuit, I would know that I can calculate the efficiency of the transformer. And who gives me those values of those R several resistances and inductances? Well, we know that we could do something called an open circuit test or a short circuit test, right. So, when I do the open circuit test, what do I do? In open circuit there is no load, that this guy is just open, and that is why we call this the open circuit test. I apply a voltage here which is equal to the rated voltage, then most of the current consumed would just be here, and based on the measurements of the power and the current and so on, I could estimate what are these guys, what is R, what is L, just by the relation between voltage, the current and the power, that we call in our lab experiments as the no load test. Similarly, to identify the resistance and the inductance of the winding, I do something called a short circuit test, where the low voltage side is a short circuit, right. So, this guy is simply a short circuit, and I keep on increasing the voltage from 0 to a value where the current goes to the rated value. That is usually typically given in your problem statement, or even if I look at a physical transformer, I will have it as the rated current, the supplier would give me with some. So, once I have the rated current going through this I1 and I2, then this becomes a little negligible, and all the parameters which I measure or all the losses would mainly be accounted in I square R losses in the primary winding and I square R losses in the secondary winding. And doing just these two experiments would give me all these values of R1, L1, R2, L2, R0 and L0, right. Okay. So, this is the process, the open circuit test, the short circuit test, I identify parameters. So, once I identify all these parameters, the calculation just becomes now a basic problem in circuits, right. So, I can just look at the circuit and all these problems translate to, so this is given maybe possibly with a certain power factor, or it just could be a resistive load. So, I am just solving problems using a pen and a paper. So, what have I done? I have looked at this guy, the big transformer which is sitting at a substation. I want to do experiments on this, which will give me answers on how this transformer would behave to different changes in the load, no load from full load, different power factor, resistive load, inductive load. All these experiments I have translated to simple experiments which I could just use a pen and a paper and possibly a calculator. And that is the beauty of the model, right. I can answer all the questions without having to touch the transformer. Okay. So, next example is something which is very familiar to us, something which we learn in high school, a simple pendulum. Well, by construction it has a mass m, a little string L, hinged to a pivot point P, and we all know that if I just start from this position given theta, I just let it go, it will just keep on oscillating back and forth around its equilibrium point, right. Okay. Now, how do we explain this dynamics or explain what this pendulum does as a mathematical model? Okay. Let us go back to high school physics for a while. The purpose of the model again is I want to study the motion of the simple pendulum. How would it behave if I release it from theta of 5 degrees or theta of 10 degrees or 90 degrees and so on. I define the relevant boundaries of the system, and what is the structure of the system? In this system, I know that there is some kind of energy transformation happening in the system, right. So, if I see here, it goes all the way here till minus theta and comes back, and at this point where it stops and goes back, that is a point where we have a complete change from the kinetic to the potential energy. The kinetic energy goes to 0, all the energy is the potential energy. This is the point where all the energy is into the kinetic energy and back and forth. So, the system just oscillates between points of maximum potential energy to maximum kinetic energy and so on. Okay, we will see how that looks mathematically. Okay, as the structure is similar to a rotational mechanical system, right. You have rotational motion, possibly a torque, external torque, or the system's own torque because of its inertia and so on. Neglect friction, I just draw something like the free body diagram which I am used to in my 12th standard physics. I have the rotational torque, there could possibly be some frictional torque, moment of inertia j, and some angular velocity omega. Okay. So, the variables of interest here are, I would, as in the car I was interested in how the position and the velocity evolves. Here I would be interested in how the theta, the angular displacement, and the angular velocity evolve with time based on these parameters of the system, the m, the l, g is naturally the acceleration due to gravity. Okay. Again, just if you recollect those basic building blocks in a mechanical system, I had the inertia element modeled as torque is related to the angular acceleration via j. And again, if I just recollect some of my high school physics, I would know that the moment of inertia is ml square. Okay. Now, I also in addition have gravity, right, in my system, and the torque due to gravity would be in this direction and can be easily computed to be mg sin theta, right, multiplied by a L. So, this is my gravitational force mg. The force in this direction would be mg sin theta, and the torque would be given by this one. Okay. And both these torques are acting in opposite direction. So, at the moment I do not consider friction over here, it is just a lossless system. So, ml square theta double dot, the torque this guy is equal to is compensated by this guy minus Tg, and so therefore, I have the dynamics written as this one, theta double dot g over L sin theta is 0. So, this is just a lossless pendulum. So, once you leave it from this position theta, it will keep on oscillating forever. So, as a simple exercise, can we try and find out an equivalent of this kind of behavior in an electrical circuit, where I just start from an initial condition and my systems are such, or the system components are such that the total energy is of course conserved, and it also shows an oscillatory behavior. Think about it, try to do it maybe in the next class to see if there is an equivalent of a simple pendulum behavior in an electrical circuit. Okay. Next we move on to modeling friction, right. So, in addition now I have the frictional torque Tf. Again, if you recollect the previous lecture, it is modeled as a relation between the torque and theta dot by a resistive element beta. Okay. So, I will have one more equation in my, or one more term in my equation, the Tr would be the negative of Tg and the negative of Tf, both acting in the opposite direction, and I just write down the relevant, substitute this Tr, Tg and Tf over here to get a final mathematical model, something in theta dot and sin theta. Okay. So, again, so this is my kinetic energy element, this is my potential energy element, this is my frictional element, if you really wanted to relate it to a mass spring and a damper kind of system. Okay. Again, think of another example of an electrical example which exhibits a behavior like this, like a lossless behavior combined with a dissipative element. Think of it. Okay. So, something which we will do now is something outside what we have learned so far in textbooks. So, I will just briefly explain you what we are trying to do here. Okay. So, let me start with some scenario here, say where I have like a little pond here with maybe lots of water, little weeds here, little vegetation inside, and I have some small fish. Okay. And these small fish, nice little guys, they feed on this little vegetation inside the pond, right. So, this is a good looking scenario where these guys, there are a bunch of those small fish, another small fish here, some hiding inside here, and so on. So, these small fish feed on all the vegetation, and then they live happily, they multiply, they grow in population, and so on, right. So, how can I model this population? So, let me call this small fish as some small s, right, and I want to see how these guys evolve with time. And if there are a bunch of them with some initial condition, a non-zero initial condition, they have plenty of food to eat, you will imagine that they will keep on growing forever. So, this could be modeled as some constant, say I will call this k1 times s. Okay. They keep on growing forever. This is a very simple model which captures growing on forever phenomena. Okay. Now, let us see, there is another pond here, where there are bigger fish, many of them, but these fish are such that they do not feed on vegetation, but they feed on some smaller fish. And if there is no small fish here for them to feed on, it is natural that all of them will die out. If there is no food, the fish go on dying, and I will model this as minus K2 times big S. Okay. So, the first equation tells me how the small fish will grow when they, of course, I assume that they do not naturally die and they have lots of food to eat, right. So, if I write down, this will just be like an exponential growth, so the S at any time t will be S at 0 e power k1 times t. This is a solution to this equation, and then if I just draw a graph between small s and t, it might just grow like very fast. Okay. So, these guys, what will happen? They do not have food to eat, so they will die down eventually, right. They start with the initial condition, they have nothing to feed, the solution will not look very good. You have S, the big S at 0 e power minus k2 t, and with time they go smaller and smaller and asymptotically go to 0. Okay. Now, interesting thing happens when I take some of these guys, small fish, and put them here. Okay. So, this is the small fish, nice tiny little ones, and okay, say one of them could be a Nemo with no feather, one of its fins lost. Okay. So, what will happen now? So, this big fish have some small fish to eat, right. So, what we would expect to happen in the second equation? So, d of big S over dt, these guys had nothing to eat, so they all were dying, now have something to eat. So, naturally we would expect that their population will grow. So, I will write that the big fish, they come in contact with the small fish at some rate, I will call this say some k3, and you will see now that the population increases, right, because they have food to eat, they can multiply and so on. What happens to this guy? Will this guy still grow exponentially? What happens to d small s by dt? Here we assume that they never die, they have a lot of food to eat and therefore they keep on multiplying. Now, this ds by dt, which was earlier k1 times small s, will now see some decrease, and the decrease will be based on how many big fish come in contact with the small fish and at what rate. Let me call this k1. So, this equation together with this equation, this is my small s and big S. I hope you are able to distinguish between those. Okay, let me just, so this is my d of small s. Okay. So, these two equations will together in some way explain me the behavior of how small fish and big fish, their population will change with time based on maybe certain initial conditions, availability of food and so on. Okay. So, we will now, so we have just written down this vaguely in terms of some mathematical equations, right, just made some assumptions, and we assume that they grow exponentially, or sometimes they die when they have food, and or when the small fish die when they come in contact with big fish and so on. Okay. So, let us do this a little systematically and see how it goes. So, these models are typically referred to as the predator prey models. So, what is this? So, there are two species, one of them serves as the source of food for the other. So, the bigger fish are the predators and the smaller fish are called the prey, and this prey, they feed on vegetation. Okay. So, how do we go about describing a model for this? Okay. So, earlier, right. So, these are based on certain assumptions and observations. Okay. So, we make the following assumptions when we derive this model, that the prey birth rate is proportional to the size of its own population, and the way the prey die is only when they come in contact with the predator, and therefore, their death rate would be proportional to in some way to the size of the predator population. Okay. The third assumption we make is that the predator birth rate is proportional again to the size of both predator and the prey populations, because when they are in contact with each other, they have food to eat and then they could multiply, right. And the predator death rate is proportional again to its own size. Further assumptions are that the predators have nothing else to eat except the small fish. The big fish have nothing to eat except the small fish, or in other words, it means that the predator species is totally dependent only on a single source, the small fish, for food supply. And the prey species are such that they have unlimited food supply and nobody else eats them except the big fish, right. There is no other threat to the prey apart from this specific predator, which is the big fish. Okay. So, let us say I want to define, these are my system variables set in a way, x t, the population of the prey species at some instant of time t, y t, the population of predator at time t. So, based on how we derived the model previously, dx by dt would be some constant alpha greater than 0, which will this first term will denote how the predator population increases, right, when they are on their own and they have a lot of food to eat. The second term minus beta xy captures how their population decreases when they come in contact with the bigger fish or the predator. Okay, this next expression dy by dt is minus of gamma y, which means that the first term means that they will die in the absence of food. The second term captures the increase in their population when they come in contact with the prey or the smaller fish and how their population expresses. And all these parameters alpha, beta, gamma and delta depend on how fast they die, or how frequently the predators and the prey they come in contact with each other. All these are like greater than 0. Okay. So, these equations are usually referred to in literature as the Lotka-Volterra equations, right. So, again this just rewriting what we just said earlier. In the absence of predators, what happens to the prey? In absence of prey, what happens to the predators, and so on. Okay. If I were to just look at the graph of what happens, right. So, let me say that if I were to just write down these things. So, if I say, well, what if the initial condition is such that x equal to 0, y equal to 0? Well, this means nothing, right. What if say some x is 1, say 15 and y is some 25? Who will increase first, who will decrease first? Let us say for example, if I start with say something x is 100 and y is say 10,000. So, what we would see initially is that there are lots of big fish to eat the small fish. So, you will see a drastic reduction first in the size of x, right, and then now these guys will have less food to eat, then y will go down for a while, and if y goes down, these guys will increase, and then they will keep on increasing and decreasing forever, unless there is a point where if there is some number x star and y equal to y star, they start from these numbers and they remain there forever, which means that if x star is constant for all times, y star is constant by all times, which means dx by dt will go to 0 and also dy by dt will go to 0. Okay, let us see if this is possible or not. So, I have two equations here, alpha x plus beta, alpha x minus beta xy going to 0 and minus of gamma y plus delta xy going to 0. Okay. So, the first equation would mean x alpha minus beta y is 0, right. The second equation would mean y minus gamma plus delta times x is 0. Okay, we are not interested in this solution x equal to 0 and y equal to 0. Therefore, the solution would be y is alpha over beta and x, well, let me call this star because I am just looking at this solution when dx by dt goes to 0 and dy by dt goes to 0, right. Okay, so, this x star would be, if I rearrange terms, I will have gamma over delta and y star would be alpha over beta. So, if my initial conditions are such that these two things hold, then my population will just be the same throughout. That is what this model tells me. Okay, what happens for any other values? So, this point here, the center point is the x star y star, is somewhere here. For every other thing, I will just see that the population of x increases, then because x increases, y will also increase, but when y increases, x will see some decrease, and so on, right. There will just be some oscillatory kind of behavior depending on where you start. If I start here, then I will just follow this curve here. If I start close to here, I might just have curves which look like here, right. And if I start here, I will just remain here. There is no other thing because I cannot go here because x and y can never be equal to 0, and I do not even want to start over here. So, these are fairly good conditions where I start at some point and then I just keep on revisiting the same point over and over again. Okay. So, this is just simulations for some certain values of alpha, beta, gamma and delta. So, this is what we call as a fixed point or an equilibrium point when dx by dt goes to 0 and dy by dt goes to 0. So, this is like the equilibrium points, and we will define this eventually more formally. Equilibrium points, they are also called fixed points. So, do not worry about this now, but we will define this formally a little later, right. So, this point is 1 comma 1 by 2. Okay, maybe we will also share the code of how to draw these kind of pictures just for your own understanding, and all this could be drawn quite easily in MATLAB. Okay, so is there any drawback of the model, right? When we look at the steps of the model, we say, oh, step 5, step 6, step 7 says, okay, come to the mathematical model, and there is another step which says validate your model. Now, if I say validate my model, will I, if I just go to a pond, I just buy some, I just own a pond for a while, there is vegetation, I buy small fish and big fish, and I say, well, I do these experiments, will this hold true? Well, they may not, because the assumptions we made are really strong. Now, let us see if we need to make some more assumptions or relax some assumptions, or maybe there should be some stronger assumptions to arrive at more realistic models. Okay. So, the drawback of the previous model was that the prey population would grow unbounded in absence of predator, which means they would never die by themselves, which is contradicting to nature. If there are, there will be people, there will be the small fish who will die naturally, and therefore, to make it realistic, we replace the exponential growth term, right. So, earlier we had dx by dt was alpha x, which represented an exponential growth in population. Now, we will also add some term which will take care of the death rate, and say that is some constant a multiplied by x square. So, therefore, if you look at this equation, if there is no big fish, y goes to 0, and in the absence of y, the prey population, well, it could stabilize at some value. It will not be that really large number of fish, there is not enough to eat, but we will, so those assumptions are a little unrealistic. So, this is an assumption which will be closer to reality or which is sustainable in the environment. Okay. Now, similarly, if we say that the predator, we assumed earlier that it will of course die naturally, but if what we also assume that if there are no small fish, they will just die because they have nothing to eat. That is also a very strong assumption. But if I say that the predator has some other alternate source of food, right, than the predator population, then they will not go to 0 due to starvation, right. So, mess is not the only source of food for hostile guys, so they could go out, they can live much longer, right. So, that I would account for saying dy by dt. This takes into consideration my increase in population because of the small fish. I modify this a little bit to take care of the account of the natural death minus by square, and this is the increase in population when I come into contact with some other restaurant food, not the mess food, right. So, in this manner we could model complex food chains. We can just look at some more assumptions, some things could be based on observations. We could also model what if there are multiple species interacting with each other. That is how the entire ecosystem of the nature is built, right, that one species is depending on the other species for survival, right. The tigers are depending on deers are depending on trees, and so on. So, all these nice kind of natural balance equations can be captured just by observations and then writing down in terms of some simple differential equations. Okay. So, what we have learned so far is very general notion of systems. What could we do with systems in terms of control, open loop control, we had closed loop control. We had classified systems into two types of physical systems which we dealt extensively were electrical and mechanical systems, and we also see well of how to build models or approximate all this real world phenomena in terms of some basic elements from electrical and mechanical systems. And even if I do not have these basic electrical and mechanical systems, I could still model systems in terms of some kind of differential equations just by observation and looking at some facts which I know that all living beings will die eventually, they need food to survive and so on. Okay. So, next lecture what we will talk is before that we will do some problems, and after we finish with those problems we will do something called as linearization of nonlinear systems. Most systems we encounter are essentially non-linear. How do we linearize them and how does the linearization helps us in analysis? We will just look at why is the linearization required, and then we will recollect some tools which we learned in math or even in signal systems course, the Laplace transforms, its properties, inverse Laplace transforms, and why do we need Laplace transforms and what is its relevance through the rest of the course.